says the following. A certain car is capable of accelerating at a uniform rate of 0.85 meters per second squared. So right away, please, 0.85 meters per second squared. And it says it's accelerating, so it's positive. If it said it's accelerating negatively, or if it said it's decelerating, then it would be negative. Okay, it then says, what is the magnitude of the car's displacement after, or as it accelerates uniformly from a speed of 83 kilometers per hour to 94 kilometers per hour? So what's my VI? 83, good. And what's my VF, Emmett?
94, but you have to change that to meters per
Very
second.
good. Good note already, Emmett. Notice, look at your units, please. I would convert that to meters per second for my velocity for both of those. You gotta have those numbers in there?
No, I didn't because I just couldn't give up.
Okay. Well, next time, try not to give up.
Can't give up.
No, I actually got another question.
Okay.
The problem with that,
People,
I used the equation VF equals VI
Oh.
plus 18.
can you hold on 1 second? Come on. Not cool, guys. Not only is it disrespectful to me, but to him also. Continue, or start over, because I didn't hear anything you said.
Okay, so the problem before that, the first problem with the homework,
Mhm.
I used the VF equals VI plus 18 formula,
You talk about number 3 or number 2?
number 2.
Number 2.
Yeah. But
For the one that the car is traveling initially?
because it said initial speed and then for you to find the final speed, but I used, is the speed the same thing as velocity or not? Because I look confused.
You're asking for displacement.
No, for number 2 they're saying,
Is
number
it
2
fine?
says what is the final velocity, what is the velocity at the end of the acceleration, right? You're given a distance of 245 meters. You're given a uniform initial rate of 7 meters per second, that's your initial velocity.
Wait, what?
You said number 2 on page 58.
55.
Oh,
Yeah, they used the
Specify. We are
word
58
speed. They didn't use velocity.
Yeah, so I was.
But they also they
I
asked for
used the velocity
displacement.
problem.
okay.
So
But they asked for displacement, so what do you do then?
It's contradictory of what you would think. I understand what you're saying completely, because we use the term velocity with displacement, right?
Yeah.
They tell you its initial speed is 4.3, acceleration of 3, find the final speed after the displacement,
Yeah.
and the displacement after 5 seconds. So I would just use your VF equals VI plus AT to find the time, to find the final speed,
Yeah,
and then use VF squared equals VF squared plus 2AX to find the displacement, or X equals VIT
yeah, that's
plus 1AT squared, yeah.
alright, so.
I agree with that.
But you only like,
Yeah, guys, this question is very valid because it gives you speed and it says find the displacement. Okay? Now, the only reason they can do this is because it doesn't say anything about changing direction. And remember, if your speed is 50 miles an hour and your velocity is 50 miles an hour, they're the same thing as long as they're going in the same direction. So there's no turning involved at all here. Okay? So it's not going to affect it. But that's a good question here. Can we finish this one or do we know what to do here? We're going to go through the quick? Okay? Helen?
Wait, can I just ask like a quick question?
About?
For number 4 on page 58, it was like, I use VF squared equals V, down VI squared plus 2AX, but like someone else told me that they like switched the equation around before they even started it. Like I just plugged them in and then.
Doesn't matter, either way it's
You
fine.
do that?
Yeah? Guys, again, it's up to you. You can solve for the variable first and then plug in numbers, or you can plug in numbers to start and then solve for it. There are certain times where it's easier one way than the other, and you're going to notice that on your test and stuff. Because I'm going to ask you a problem that says like, find the acceleration, right? So say you have a problem, and here's the formula you're about to use. All right, and you're given the displacement, you're given VI, you're given VF, and you need to find the acceleration. If you solve this for A initially, you have a generic solution that says A equals VF squared minus VI squared all over 2x. Right? That's that generic solution, as opposed to plugging in the numbers first and then solving for A. It is very useful to do this if you're given, say, 5 different scenarios. So if I give you VF, VI, and X for part A, and say find the acceleration, and then in part B, all I do is change up VF. You don't want to have to plug the numbers in again and do it over again. You can just simply plug it in here. That's why this is important. But again, it doesn't matter. The answer is not going to change. It's just that if you plug in numbers first and you have several repetitions of that problem, it's going to take you a lot longer.
Yeah,
Okay? That's the benefit from it there. All right, with that said, though, let's take a look at this problem here. This problem is asking us to find, this is number 4, it is asking us to find the magnitude of the car's displacement. So for this problem, we're looking for x. All right, we're looking for x.
So I did like Ellen did, I did VF squared,
Mm-hmm.
equals VI squared,
Good.
plus 2.
2ax.
2ax, yeah.
Okay. What did you get when you converted here, Evan?
I got 23.06 for the VI,
Uh-huh.
and then 26.11 for the VF.
That sounds good. Remember yesterday what I showed you guys for converting if you need help? What can you do? Check on Google, check on your calculator, okay? You can do that. But that's correct. Those numbers do ring a bell in my head. So what did you do at this point?
I just plugged it in.
Okay, so as I said, let me just plug them in. Again, well, you can do that if you want to. You could solve for x here by subtracting vi squared. You get vf squared minus di squared. When you take this and subtract it over. Then if you want to get x by itself, divide by 2a, because this is now gone. Divide by 2a, and that's what x turns out to be.
So is that what I have to do to find?
Again, you don't have to solve for x and then plug in numbers. If you want to, you can always plug in numbers first and then solve for x. It's up to you, whatever's easier for you. Okay, personally, I think this is more powerful of a method. And if you want to do anything with physics or computers and stuff, you got to start to learn how to do this. Because computer coding is all about writing formulas, okay, and algorithms. They can sit there and plug in different values. Okay. Other questions on there. Now again, you would plug in this quantity, and this quantity here, these 3, to solve for your x. Other ones that maybe weren't understandable or were a little bit vague maybe on the homework. It should have been straightforward for the most part. Again, converting units is always a little bit of a, not challenge, but a stagnation point. Yeah.
3A.
On page 59. All right, 59, 3A, it says, Nathan accelerates his skateboard. Come on, next page. Hold on, guys. Nathan accelerates his skateboard uniformly along a straight path from rest to 12.5 meters per second in 2.5 seconds. What is his acceleration? What was the question?
No.
Remember the most basic formula we started with was this one. Okay? Or you can use this.
I think I got confused because
Either one. You're starting from rest. Okay? He's accelerating to 12 and a half times 2.5.
I wrote all that down. Wait, did they use speed again? Because I think that's my.
Maybe that's why. Let's see.
I think that's why.
No.
No?
No. Not at all. So solve for A. You can use this formula here at 3 because it's already solved for an A. It might be easier. Or you can use this one and just solve
Oh,
for it.
I know why. The change in V, is that VF minus VI or VI minus VI?
VF minus VI.
Okay.
Okay, VF minus VI. It should have been a positive acceleration. So it'd be 12.5 minus 0.
So that's what.
All right, let's get started with today's.
You're being recorded.
Now, today's topic is 2-3 in your book, in case you want to reference it.
Stop. No.
So last year I played the song Free Falling as we were starting. Everybody gave me like a dirty look.
I love that.
So
John
that's
Mayer
what we're
version
recording.
and John Mayer version.
So I didn't actually play it. but
John
I did
Mayer
it.
is so much. That would have been cool. Mr. Howell.
As we were coming in, just having classes,
Yeah, kids like for us.
Tomorrow.
No, this is you guys.
Tomorrow, maybe we should get Jack Mullen in here on this.
Jack Mullen jams it out.
Moving her hair.
All right, so the idea of free falling objects is very apparent all around you. Okay, if you take an object and you throw it up in the air, as it's coming down, it's considered to be in what's called free fall. If an object falls from a building, it's in what's called free physics, which is what this is, there's no calculus involved, you can't really account for air resistance, okay? Because it's something called a derivative, or it's a function of its velocity. So what we're going to do today for the year, we're going to assume there's no air resistance at all affecting the object. Because if there were, there's air inside. So if it were, we wouldn't be able to solve it with just our basic kinematic equations, all right? So we've got an object starting on a cliff, and it's just dropped off the edge, okay? What I want to do is discuss several things. First, the speed at which it hits the ground, like right before it hits the ground, the terminology is called the impact speed. So let's write that down here. Right before it hits the ground is called the impact, and we'll say velocity actually, because we're using a direction down, is the impact velocity. So when a problem asks you, find the velocity of the object right before it hits the ground, that's what you're looking for. You're not saying like, you know what I did last year? I told this whole thing, and some of my students would put 0. They'd say, well, hit the ground, so it stops. That's the velocity. So I want to be very clear with what I'm saying. When it says find the impact velocity, or find the velocity as it hits the ground, it's an actual number. Sure, after it hits the ground, it's going to stop, and it'll be 0. But, you know, it is an actual figure. Next. If you toss an object up in the air, what can you say about it along its path? So I toss it straight up, and it comes straight back down. What's something you can say about the object's movement, or the path, or anything about it? Steph?
I forgot what I was going to say. I was going to say what goes up must come down.
Sure, good. That's fine, no. And what does that have to do with?
That has to do with like
Gravity. Light, and what is it? Gravity. Very good, you mean gravity. What else? Nicole? Good, good. You're going to hear that. One more time, Nicole. Let's stop talking others.
Nikki.
If it lands right where it started, zero displacement.
Yeah, you toss an object straight up, and it gets tossed from my hand right here. It comes straight back down. There's 0 displacement. Very good to know.
It's not
Awesome.
possible. You can't throw something in the air and it lands perfectly right where you threw it. No. Okay.
Pretty good.
Like,
There we go. Pretty good. Now, what else about it? What else about the object while it's on its path? Other information about the object.
Okay, it's going faster up than down. Or is
No.
that just, oh no, the other way
it's
around?
gonna slow down when it reaches its highest point. Right?
Okay, until it reaches its highest point. And then what's going to happen?
It's gonna speed up,
Like a roller coaster.
It's going to speed up coming.
Down.
down.
What happens at the top?
Stays there.
Yeah, it stays. It pauses. So, when an object is thrown, which I'm going to throw in the back of the room pretty soon if you don't stop talking.
Hey,
Focus.
those three shouldn't sit next to each other.
I'm going to speed you up very soon. And I can think about that. Come on, people.
They play with cylinders in class.
Now, we throw an object up in the air. It gets to the top of its path. It must pause for some instance in time. And think logically. On the way up, the velocity is positive. Then it stops, and then it becomes negative. You can't just go from positive velocity to negative without having a 0 in between. Okay, it's a continuous thing. You go from a positive quantity, it's getting slower and slower and slower. It has to stop, and then it starts to speed up in the negative direction. So at the top of a path, when you toss an object up, the velocity equals 0. Very good thing to note. So if we're looking at a problem where it starts at the bottom and it says, find the time it takes to get to the top, you would call this VF, and you would call this like your VI, whatever that turned out to be. So keep this in mind when we're doing these problems. When it pauses at the top, its velocity is 0. Erica.
For an object that's starting to like go up and then like gravity starts to slow down and then like it finally stops, would that be like resistance or would
Yes.
that be the both?
Yes, that would be negative acceleration or in the sense of resistance. You figured it that way. Yup, that's fine.
The
So
bottom.
it would, whatever the number is we have, like whatever is given. So. Steph had her hand next.
Okay, I have a question about like when you have negative velocity. Do you have to think of it as like absolute value because
You can think of the speed as the absolute value.
but would negative 50 be faster or slower than negative 20?
Negative 50 is faster in speed, and it is more negative in velocity.
But it's still, even in velocity, it's still going faster, right?
Sure, but I would say it's more negative, to be clear. Because when you say it's faster, you're really indicating speed, not necessarily its,
What is it?
not necessarily its velocity.
Condition of classroom.
Super nosy. Helen.
Say something falls off a building, and then like the velocity going down, like the final velocity, would it be like reflected and like the bounce back up? Like would that be?
Theoretically, yes, due to conservation of energy. Realistically, no. It loses energy when it hits the ground. The object actually contorts itself a little bit. Energy goes into the shape being misformed. It's very different, but theoretically, sure.
Okay.
Okay? Yes, Will.
There was a Snapple fact that said that if you put up a penny up the Empire State Building,
What did it say? Or what?
it could fall off the one that it could go right in.
Okay, it's funny. The first example I did today is dropping something off the Empire State Building. So if we get to that, hopefully we'll go through it. But it is a myth. It is a myth, that one.
It
Okay?
is. Wait.
It is or not?
Next question. We're getting started. Next question.
Throwing something. Okay, something's falling off a cliff. This happens. But what if you're throwing something?
Yeah, that's okay. Next chapter is two-dimensional motion, where you throw it at like an angle, like a football. The problem is that you guys never learned trig last year. You don't know, right? Nobody's learned right triangle trig yet.
We're doing
In that. You're doing it this year. Are you doing it now?
No, this year.
This year. So what I'm doing is I'm playing around that. So we're going to go back to that topic once you guys learn trig. Okay? I'm being honest, that's the reason we're not going into that just yet. This is called one-dimensional motion. Yesterday, we talked about cars moving horizontally. We talked about cars moving horizontally. Today we're talking about objects moving vertically. Either way, it's only one-dimensional. It's not at an angle at any point in time. Okay, we're not looking at angles right now. It's not any harder, really, but then you have an x direction, a y direction. You need to use sine, cosine, tangent, which is not difficult, but without having learned it, it's going to sound like a foreign language for you. Okay, so I'm going to wait on that one. Let's get into our first example. So, I'm going to dictate. Please write. An object, I'm dictating, is dropped.
Democratic dictatorship.
Dictate also means speaking, right?
Yeah.
What?
Okay.
You don't
Dictate means
speak, you
speak.
dictate.
An object is dropped from the top of the Empire State Building. From the top of the Empire State Building. And in parentheses, you could put 443 meters. That's how tall it is. That's the correct number.
Wait, again?
443 meters.
What's that?
Metros.
I'm not even impressed.
Okay.
Exactly.
It lands directly on the ground below. Determine the velocity of the object when it makes contact with the ground, which is that impact velocity. Determine the velocity of the object when it makes contact with the ground. Second part, how long does it take?
Wait, can you rephrase that?
Determine the object.
Determine the velocity of the object when it hits the ground, and how long does it take? Okay.
Yeah, what I really understand is why we use velocity and displacement.
Displacement.
Like
You know what? This question will probably help you with that. It's funny you said that.
you put like it's like the velocity of the impact. Like, does that mean like how long it took to get, or like what it was to get down there? We know that.
7 minutes.
No, velocity is like the speed almost. We're asking what the rate of change is when it hits the ground. How fast is it going? Displacement is how far it's coming.
We don't use it.
We have displacement. It tells us the height of the building is how tall. Okay. Let's draw a picture, please. Stop, Alan.
Sorry.
I don't find this funny. I kind of want to learn this.
She's so weird.
So, the building is 443 meters tall. Okay, 443 meters tall. That's all the info that we're given. That's it. No other information is given in this problem. You can notice that. All we're told is that it's dropped. Now, Helen, give me one piece of info in addition to this that you got from the question. If it's dropped.
That the initial is 0.
Good.
Wait, but do you suggest that we draw a picture usually? Do you
I
think
always
that
do.
helps?
I always do. I mean, it doesn't matter.
It's easier.
It's up to you. It really sometimes does clarify some things.
Okay.
We're looking for final velocity.
If you're a visual learner,
Yes.
Displacement's
X. What's X, guys?
443.
Negative 443.
Negative. you. Negative. Which way is it moving?
Down, achieving, Brooks.
South.
All right. Now, here's the next piece that I don't expect you to have known. Some of you might know. What is the acceleration due to gravity? Anybody know this one?
No, negative
9 point. Very good. Very good on it. The acceleration of gravity is called G, which is really negative 9.81 meters per second squared. Isabella, focus. Remember yesterday when you wrote your 9 like a G? That's why I said that to you. Because we're going to use G, and G happens to be negative 9.81. So try and write them differently, okay?
Is that just like a given?
Always, always, always. This is something you need to box in big letters. On Earth. On Earth. It will always be the acceleration due to gravity. If you were on the moon, it's about 1/6 of that. Which is why you feel much lighter on the moon. You see the little like funny cartoons of people like jumping around the moon, like prancing. Because they're only 1/6 of their weight. So on Earth, you weigh 150 pounds. On the moon, it would feel like you weigh 25 pounds. That's it. So you'd be able to jump like, 10 feet in the air. Because weight is a function of gravity. All right, now, the problem starts by asking us to find the final velocity, right? How do you know the final velocity is what we're looking for? Hands. Chaz. Good, when it hits the ground. And we are looking at a segment of this, from here to here. Now, remember yesterday I mentioned the term piecewise function. That's what this is, because you think about it already. You get on the elevator at the Empire State Building. You go all the way up to the top. That's like the first piece of it. Then you stop for a second. As soon as you drop it, you're starting the second portion until it hits the ground. That's the second. And then it'll bounce over here. I don't care about where it bounces to afterward. I don't care about the path it took you to get up. All we care about is this path right here. So this is your starting point. This is your ending point down here. So whenever you do these kinds of problems, like you did with the problem set yesterday, where the person walked a certain distance, rested for 24 minutes, then walked another distance, that kind of a problem is in 3 different pieces. If you don't like the word piecewise because you're afraid of it because math makes it tough, think of it as segmented. It's segmented. There are little segments along the way. So we are looking at the second portion of the segment here. We don't care about how you got up there. We don't care about what happens to the object afterward. What we care about is the path along the way. So we are trying to find VF, which will be the velocity at the bottom when the object is about to impact the ground. I've got VI, I've got X, I've got A, I want VF. I also want time, because it said how long will it take. Okay, I also want time. Hunter, tell me what equation I'm going to use here. Wouldn't use that one. And A is delta V over delta T. We don't have time here. Think about your other kinematic equations. Help me out, Mom. Hold on, let's see.
Oh, VF squared equals VI squared plus 2AX.
Good. Let's go over why this is the choice. Take a look. We got VI is given as 0, right? A is given as negative 9.81. X is given as negative 443. So we have every single thing in this equation. And we're actually solving for VF. So we don't have to rearrange it this time. This is one of the examples where you do not have to move things around at all. Okay, you don't have to move things around. Now, what did I say yesterday or the other day when we have a VI equaling 0 or something like that? What do you do to it? Good, very good, Green. Go like this, please. VI drops off. We don't care about it. So really what we have is this formula. That's really what the formula is that we're using right now. Because the initial velocity was 0, it was dropped. It fell from rest. Okay, next. I want to get VF by itself. How do I do that?
It is by itself.
It's not.
You have to square root
Oh.
Thank you. Now it's by itself. Very good. Be careful with your answers, people. This is going to be so important here that you forget that you remember the plus or minus.
What? I don't understand.
I'll explain. We'll get there. Trust me. At the end of this problem, you're going to see why.
I like when I've been doing this square, I don't know like if this is even wrong. I've been doing the square root at the end. Does that work just
Yeah, same thing.
I like to do the multiplication and then get the square.
Again, no big deal. Take a look. Let's write down our numbers here.
Okay?
Focus. Take a look, people. If I have a negative negative, it becomes a, and you need a positive. You can never have a negative under the radical because your answer would be imaginary. Okay? It's an imaginary answer, imaginary numbers. Have you learned about them yet? Yes, no, maybe? All right, just know for now, you'll learn about it this year for sure. You can't have a negative under here. The two negatives make it a positive. And notice, look at your units. You're going to have meters per second squared times meter, which becomes meters squared.
Over second squared.
Very good, which is what we want, because when you take a square root, you'll get meters per second.
I had fun today.
Okay? Let's do this.
Right. Go get a cookie. Eat it. Lonnie freaking zombie.
Now, don't go anywhere. Give me another minute or so.
Negative 8,691.
Okay, I'm going to put the answer up though, so let's take a look now. Negative or positive 93.3 meters per second. Don't back up yet. Please, come
I'm
on.
open.
The object is traveling which way? So what is the velocity going to be? Remember you said why do you need a plus or minus in there? You got to choose which one it will be. Now, tonight, here's what I want you to finish. Find the time, please. Either using,
Wait, Mr. Howell should be 93.23.
okay, 23, thank you.
I'm open. I'm open.
And we're choosing the negative one. Either use one of these formulas, figure it out on your own, please. Use one of those two formulas there to find the time that it's going to take to land. Either one will work. One might be easier than the other. So figure that out tonight. Again, you could try both and you'll get the exact same answer. You're going to get 9.5, so you can check. I want you to figure out the time for this problem to take the ground, hit the ground. That's what the answer will be, but figure it out and verify it. That's what you got to figure out. Try and find the time.
Okay.
That's all you have, yeah. We're going to finish up the other problems.